Hello everyone and welcome to a video for the Chem 40 series. This video is really intended for the 40B students who have to crank out mechanisms. It could be used for the 41 series, though I'm not entirely sure. The entire purpose of this video is either a refresher for a lot of students on how to draw organic mechanisms, and if not a refresher, but at least some form of introduction to how to draw organic mechanisms. Um, the expectation in this video is that you are familiar with some of the organic chemistry jargon that is going to be thrown at you by me. For example, do you know what a nucleophile is? Do you know what an electrophile is? If you don't worry. That's not an issue. There are other videos that I've created that would describe what those are and what makes a good nucleophile versus a good electrophile. And I'd highly recommend you that you go back to those videos first to kind of understand that until you can come to this video to fully get an encapsulated understanding of what really should go on in a mechanism when you're proposing one and all the considerations that a typical student should kind of keep in mind when they're proposing an organic chemistry mechanism because it can get quite complex. And this is really intended for people that are in OChem 1 and OChem 2. Students that are a higher level organic chemistry, this is not necessarily a great video for. It's probably going to be very redundant. And so without further ado, let's just begin. So the very first thing that I love to do when I'm doing organic chemistry mechanisms is figure out what is the number one thing. Figure out my nucleophile. I'm going to call it as nuke. My electrophile, ELE, and my leaving group, LG. And very briefly, my nucleophile is a nucleus-loving atom. In other words, it has more electron density and it wants to get rid of that electron density, and it's attracted, because it has higher electron density, to places with lower electron density, aka the electrophile. So this is going to be low electron density, ED. It's going to be high ED. Remember that electrons are negatively charged. So if you have higher electron density, you could assume that these guys are either partially negative or have a negative charge. Additionally, with an electrophile, because they have less electron density, it is pretty fair to assume that they are either partially positive or have a positive charge. And so that is exactly the first thing that I'm going to do. I'm kind of look through my entire molecules that I have, my reagents, and say, well, which one could be my nucleophile and which one could be my electrophile? Now, sometimes it's not easy because you could really have complex molecules. And sometimes there could be many sites for nucleophilicity and many sites for electrophilicity. And so that boils down to another concept that you're going to have to keep in mind, which is the following. You have to figure out the stability or reactivity, stability/reactivity of your reagents, And so to put it simply, that's just saying which is a better nucleophile in the molecule that you have and which is a better electrophile. And so, for example, and totally hypothetical, let's say I have a molecule that's a dihydroxyl, but instead this is deprotonated. The O is deprotonated. And so if I were to ask you, where are the nucleophiles of this molecule? Well, it's plural, so you'd say, well, there's two nucleophiles. But then if I were to ask you what's the best nucleophile in this molecule, you'd probably point at this one because it's a harder nucleophile. It has more electron density to it. It's negatively charged. It's more reactive. And so one of the best ways to figure out your reactivity of your reagents is to kind of go back and figure out, well, what makes a good nucleophile? And there are several things that make good nucleophiles. And one important thing to remember is that nucleophilicity and electrophilicity are kinetic properties. So you should be considering not only electronics, so things like resonance, induction, but also steric effects too. And also, alongside electronics like atomic radii, and a few other things. These are definitely not the only things that make a good nucleophile. So to be absolutely clear, do not just watch this video and think that, oh, resonance, induction, and atomic radii are the most important contributing factors to what makes a good nucleophile. Not necessarily true. There are other components like your solvent, and I'll get to solvents really quickly, but there are many components to it. And so let's say you have identified a nucleophile and an electrophile, but you've come to say that, well, maybe these reagents aren't very stable, or maybe they are very stable. And let's work with the stability component of this really quickly. Let's say they are really stable. And in that case, they're not going to be super reactive. So the more stable you are, the less reactive you are. And as a result of that, you might be concerned that, well, maybe my reagents may not react. And so what are you going to do about it? And what are some hints that could possibly lead you to an appropriate mechanism? Well, the first thing you can do when you can try, and by the way, the description of this is called activating your reagents. Activating reagents. Okay. And after you've kind of ranked your nucleophiles and your electrophiles, and you figure out which one's the best one, and you still deem it as too stable, you're going to be like, okay, well, what can I do? And the answer is, well, I can try to activate it. Activate it literally just means to make it unstable. And there's a few ways you can do that. One, you can just increase the temperature of everything. Typically, sometimes, not all the time, but you can. Temperature increases the reactivity of molecules. You can get a quicker reaction that way. The second thing, and the more definitely common thing in typical organic chemistry classes, is using acids or bases. And so acids like HA and bases like B minus or A minus can be used differently. Bases are typically going to deprotonate, right? But what are they going to deprotonate? They're going to deprotonate your nucleophile. So if you want to make something called a hot nucleophile, one of the best ways to make a hot nucleophile is through using a base, a catalytic base, by the way, not any type of base, because bases, because they have electron density to give off, could also act as nucleophiles. And so, for example, you're going to need a you're going to need a non-nucleophilic base that can specifically deprotonate at a specific pH the nucleophile that you want. And so, for example, you may come across certain nucleophiles like LDA. LDA, which is lithium diisopropylamine, is a really, really bulky nucleophile. And because it's so bulky, kinetically speaking, it's not going to be a good nucleophile because of sterics. But it still makes it an excellent base because acid base or neutralization reactions are relatively quick and also don't require a lot of sterics because it's just a proton transfer. And so for that reason, you could use something like LDA. You can also use tert butoxy as another common nucleophile that you might see. That is, or not nucleophile, sorry, a good base. And these tert butoxys, again, very sterically hindered, non-nucleophilic, fantastic bases to make a hot nucleophile. So that's base, but what about acid? Now, acids can be used for two things. Acids could be used to activate your leaving group, activate Lg, or your electrophile. So what do I mean by that? In the case in which you have, let's say, carbonyl, like that, ketone in particular, you could treat it with acid, and you get electron pushing, boom, boom, and you get something like this. Now, the thing that I want to illustrate here really quickly is that there is a resonance component to a carbonyl, and that the carbon can donate its double bonded electrons into the oxygen, and you can get something like this. And so that's important because now I have developed a higher degree of carbocation character because my oxygen doesn't want to be positively charged. It's an electronegative atom. And so it'd rather be like this more often than just typically like this. And so now I have developed a greater carbocation character on my on my carbon, whereas a regular carbonyl would have actually still been in resonance. It's not to say that it wouldn't, but it wouldn't be as frequent. So this would be a much more dominant resonance contributor. But now I've kind of switched the gears and made this one have a greater degree of significance. It's still a minor contributor, but nonetheless, it is going to have a greater significance to the overall structure and reactivity of the molecule. But yet we're activating the electrophile because in most carbonyls, you're going to do addition reactions. And so you're going to add into this portion of the carbon. What about leaving groups? I'm going to use actually carbonyl chemistry because most 40D students are going to use carbonyls frequently. What can you do about leaving groups? Well, let's say you have something like a thioester, or actually better yet, an amine, or an amide, sorry. Okay, and you get its tetrahedral intermediate, and so don't like this is not how you're supposed to draw your mechanisms. Just I'm trying to show you just a little bit of movement. Assume that you have a tetrahedral intermediate, R group, and I'll differentiate the two, or the three rather. And so what's important here is that this amide, assuming that we're going to have a good enough molecule where it can push the amide or the amide slash amine off, what you'd want it to do is you want the double bond to reform, collapse basically, and push the amine off. The problem is if I were to just leave or make the NHR leave, you're going to get NHR minus. It's super unstable. It's a terrible, terrible base. Well, it's a super duper good base, rather. It's just a terrible, terrible, terrible leaving group. Again, good leaving groups are typically very weak bases. So what can I do in this case to ensure that I can get an appropriate activation of my leaving group so that I can perpetuate my reaction mechanism? The answer is to protonate your leaving group. By protonating my leaving group, in this case I'm going to draw it right here as O minus NH plus R, and then tetrahedral intermediate. What I can do now is I can collapse my double bond and push off my amine, but now I have NH. I should actually draw it slightly different. NH and then 2, sorry, NH2R. And in that case, now I have a typical amine, totally fine, totally stable, and it's a weak base, as opposed to this NHR minus, which was way more unstable and definitely would have not come off. And so that's another case in which you're going to have to activate something. You're going to have to activate your leaving groups. These are also especially true when it comes to doing E E1 reactions. In E1 reactions, you're going to have some type of leaving group. Let's say you have, yeah, a bromine, or actually better yet, let's just say a hydrogen, or sorry, a hydroxy group. This is not a good leaving group for it to leave, and then you get a base eventually to kind of like nick off an alpha carbon. What you would want though is to protonate this hydroxy with a catalytic acid, whose conjugate base, by the way, is non-nucleophilic. Protonate that acid, or protonate the hydroxy, make it OH2 plus, in this case, OH2 plus. And now typically, these types of leaving groups will just naturally leave, leaving you with a carbocation like this. And in this case, you're going to have your base come over and just go boop. You're going to go boop, and done. You're going to create a double bond. Your internal alkene. Perfect. Great. But still, again, you are activating your leaving group. You can activate your electrophile, or you can activate your nucleophile. But there's different reagents that you can use. In a biochemical context, your leaving group that you can do, especially with hydroxys, because you have enzymes called kinases. And I will actually remove this to illustrate what I'm going to describe. Oops. You have enzymes called kinases. These guys go to hydroxy groups, and they replace them with OPI, an organophosphate. They don't really replace it. They do a reaction. This is in chapter 9 of your textbook, by the way. Chapter 9. It's all about phosphate reactions. I'm not going to go through the mechanism. I actually have a video on the mechanism, and you can watch it there. But effectively, this OPI, which realistically is like this, right, is a great leaving group because you can hop off like that. Boom. If, this was an electrophile, by the way. So let's just say ER, really for electrophile. The R is just an R group, but whatever. And if something were to come and attack it, a nucleophile, for example, that will hop off and you create a phosphate ion like that. And it's great because you have this fantastic opportunity to delocalize your electrons. And that's a little bit of your biochemical context. But it's not to say that your enzymes, besides phosphorylating things like kinases, they can definitely use a lot of acid-base chemistry. For example, your enzymes are very pH selective, and they're going to use histidine very frequently to deprotonate and protonate it. The histidine that they use typically is going to be in a very pH controlled environment, pH control, and they're going to really be deprotonating, dep and prot, deprotonate, protonate, the imidazole ring, the amine-like nitrogen on the imidazole ring because it's got a pK of roughly about 6.8. You don't need to know that, but the point being is that you're going to see questions in your 40B tests that have a histidine as one of your molecules, and I'll show you what histidine looks like. I'm too lazy to draw it, but you're going to see this molecule right here, especially at this nitrogen, okay? Right here, this nitrogen, okay? Not the one with NH, this nitrogen that will be used as a base or an acid repeatedly. It's how your enzymes work. They're pH controlled. But be very careful and be very, very aware because that's something that gets a lot of students in their classes. Um, anyway, so now we've discussed, identifying what's your nucleophile, electrophile, leaving group, how to activate them, and how to rank the relative or considering the relative reactivities between all the things that you have, and also how to activate them. Okay. The next thing you want to do is consider your solvent. And so why would I consider my solvent? So back in 40A, if you covered it, SN1 versus SN2. These are actually solvent dependent a little bit because it changes how well a nucleophile is. Remember, weaker nucleophiles go through SN1 reactions. Stronger nucleophiles can do SN2 because they can just immediately push, or they have such high electron density, they can push off the leaving group. That's important because if I have a protic solvent, it's going to be pretty bad for SN2. So SN2 likes aprotic. SN1 likes protic. What is protic? What is aprotic? Aprotic, no H bond. So if I were to put something in acetone, for example, this is what acetone looks like, and think. No H bonding. Well, there is no opportunity for it to like H bond with itself. So there's no hydrogen donor, basically, like that. In protic, there's a hydrogen donor typically. Protic, aprotic. Um, Actually, even better yet, a fantastic example of an aprotic solvent is going to be something like DCM. The reason I bring up DCM is most bio and chem students are going to take 43A. And as a result of that, DCM is going to be used um, in a few of your reactions. And DCM structure, it's polar. It's called dimethylene chloride. There is no ability to H bond, right? And so, again, SN2A product, SN1 product, super important. Keep that in mind. What's next? Kinetic and thermodynamic products. This is more something that will be covered in 41 series, but definitely good for a 40A student to know. Kinetic product, typically at low temp. Why? Because the activation energy is lower than the thermodynamic product. This, let's say, is the kinetic product, Kp. Let's say this is a thermo product. Thermodynamically speaking, and let's just say these are two SN2 reactions or something like that, okay? Because they're just concerted. There's one step. Look, both reactions have a difference of delta G that is negative, okay? But with that being said, one is much more significantly better. That is the one that's way further down compared to its reagent or the reactant in the product. But the activation energy here versus here is fundamentally different. This has a smaller activation energy. And so it means that this is quicker to get to, right? So the rate of the reaction is faster. Rate is faster. Whereas the product here is more stable. So stable product, stable prod, and faster rate. Okay, and so why can temperature kind of determine whether or not you're going to get a rate that's faster slash slower, or a kinetic product versus a thermodynamic product? In a low temperature, you really don't, your molecules don't have the ability to kind of reach higher activation energies, and so they're going to try to react in a way, or they'll, assuming that it's still like in a liquid solution, it's not like you've frozen everything. Okay, so not some solid state chemistry. Um, your lower temperatures may only suffice to provide enough energy to get certain molecules up to get to its kinetic point for this. And so you may get a reaction that's like this. You can get a kinetic product instead of a thermodynamic product like here, where you need a lot more heat, a lot more energy to kind of get all the reactants to get to their really highly reactive and unstable transition state TS. And so you can get a kinetic product. Where are you going to see these in 4DB? Definitely going to see them in enolate chemistry, especially asymmetric enolates. Asymmetric, I don't know how to spell asymmetric. I'm illiterate. Asymmetric enolates. Example, something like this. Okay, you have the hydrogen here. You have something here, and you have an H and H. And enolate being that you can kind of deprotonate it. So these are alpha carbons, alpha and alpha. You can also see it in butadiene chemistry. There's going to be a ton of kinetic and thermodynamic products. So be careful of that. And lastly, you'll see it with molecules like this. When you have conjugate addition, you could either do 1,4 addition or 1,2. You're a 40B student though. That means that you're not going to have to worry about 1,2 addition. So you're only going to be doing 1,4, which is called conjugate addition. So you're only going to be reacting here. Okay? To the delta. I want to say delta because this is alpha, beta. That's delta right there. To the delta carbon. Okay? But these, you will definitely have to know asymmetric enolates. And it's just super duper important. And so that if you get low temp, you're going to get kinetic products. If you get high temp, high T, what are you going to get? You're going to get the thermodynamic product because you're giving it enough energy. You're giving the system enough energy to get to its high activation state and actually finally reach down. And so let's say maybe it does become a kinetic product. It can go back into its reverse reaction. So go back to the reactant, decompose, and then go through this reaction mechanism instead. Boom. You'll learn more about what would make, or you'll learn what type of reaction would create thermodynamic and kinetic products. But I'm just letting you know that these are the molecules in which you're going to see it in for your class. And so it's typically for the enolate going to be the more substituted end. And I'm not going to go into in depth about enolate chemistry and why it is and why it's not. But I'm just giving you a very brief fundamental overview. It's going to be the kinetic, or sorry, the more substituted side is going to be the thermodynamic product. Um, there are reasons for it, um, but yeah, that is going to be a much more stabler compound right here. And when you're doing kinetic products versus thermodynamic products, the type of catalyst you use or activating agent is going to be important. Catalyst. And so for kinetic products, you want to use sterically bulky ones. Sterically bulky. Why? Because inherently, you're going to reduce the collision frequency of your molecule, or not necessarily collision frequency, but appropriate or good collision frequency of your molecule, so that you're only going to get the more open or the less sterically hindered sites, which are going to be kinetically better because they can react quicker. The two components or the two atoms can hit one another better. So where is a sterically bulky base, for example, that you could use in enolate chemistry? LDA. I keep on referring LDA because you constantly use it. Okay. Um, a little word on bases and acids. Be super careful about what bases and acids you propose in a class or when you're doing these types of chemistries. For example, like I said, you want your bases and you want your acids to be non-nucleophilic. So you could say, oh, I want to use a hydroxide base, but hydroxide is also a good nucleophile. And so as a result of that, you could engage with its nucleophilicity property as well and get some reaction that is unwarranted. And so be very careful when you're doing acid-base chemistry to really make sure that you're not confusing something like hydroxide as a base instead of it being not an acid, but a nucleophile. And so that brings me to my next point of figure out whether or not your reagents are going to do acid-base chemistry before they react. And so a lot of people like to say like, oh, I can make a pep or a sorry, I can do some peptide chemistry by doing this and getting these molecules to react with one another. Yeah, that's very wishful thinking because what ends up happening typically, or rather, sorry, this is a terrible example, but people typically think that I should have changed the reactants. Whoopsie. Sorry, this is it. Okay, you have your amine, you have your carboxylic acid. Your carboxylic acid is actually more reactive of a carbonyl derivative than your amide would be if you react these two things together and get an amide. But the reaction wouldn't happen like this, not like this. And you might be like asking yourself, well, why the heck not? It's because of acid-base chemistry, it's quicker. And so what would quickly happen is that you're going to neutralize your carboxylic acid here, and you're going to protonate to get an ammonium. And womp womp, now you've removed your nucleophile and created this other nucleophile that really isn't a good one. It's basically resonance stabilized. But point being here, really recognize your acid-base chemistry when it comes to your reagents. Okay, so acids and bases can be used as catalysts and activating agents, but at the same time, if your compounds, if your nucleophile, if your electrophile have um, as a molecule have acid-base components to it, they could definitely skew the way your reaction would go. So if you were to be proposed this type of mechanism on a test, and you were to say, oh, you're going to form an amide, you'd literally be wrong because what's quicker is a neutralization reaction. So remember that. Neutralization reactions, or rather AB chemistry, acid-base chemistry, is quicker. And so what would I have to do in a case like this? There's a few things, but to be really 40B oriented, you could basically just say, oh, why don't I switch off my group right here with an OPI and create an acyl phosphate? You can. Other things that people do is they react it with acid chlor or make it into an acid chloride from thionyl chloride. Other things people do is use peptide coupling agents. But again, we're going off topic. And so to get back on topic, really just consider your acid-base chemistry. Not only does that matter in the case of nucleophiles and electrophiles, but it matters in one other context, your pH. Your pH will determine whether or not how well of a nucleophile you have. And so a lot of your body is buffered at pH 7. And so to be 40B specific, right, you really want to understand your reagents in the sense of pH 7. It's like your human body is like 7.35 to 7.45. If you had a pH of 7, literally 7 in your human body, it wouldn't be the best. It'd be actually kind of low. But point being, you really want to know your pH because your pH will actually determine your ionization state. Remember, you're in a buffer. Because you're in a buffer, um, you have a certain amount of you have a certain amount of protons and a certain amount of hydroxides available. You want to make sure that if the concentration of hydroxide is too much, you appropriately understand what ionization state you're going to be in. So, for example, the average or approximately the pKa of carboxylic acid is 5. Okay. So in pH 7, that's going to be deprotonated because it's lower than the pH that I'm set at. And so you're going to get COO minus. So note that if you have some pH and your pKa is lower, you're going to be deprotonated. If your pKa is higher, you're going to be protonated. And so that's why amines are typically seen as NH3 plus. They're going to be as an ammonium. Um, and so yeah, that's something super important to recognize because now I have an NH3 plus. I don't think the majority of the amines here, if they're like this, can be a nucleophile, can they? They cannot. Other times this is important is with a lot of carbonyl or carboxylic acid derivative chemistry. Remember, this guy is really this guy. And so if I wanted to react it with, let's say, an amine, well, how lucky would I be to do that? I can do this with this molecule. I can do this. I cannot do that. I would have to activate this first. Okay. Again, I did bring up the example that these two normally can't react with one another. There are actually instances in your body that can do it. Okay. But that's getting too far advanced in bioorganic chemistry, and you don't really need to know that. Just for the most part, know that those two things can't react because acid-base chemistry dominates in that sense. It's just much quicker. And finally, getting to the very end of this, besides temperature, besides acid-base chemistry, besides your solvent, besides ranking your reactivities, the last few things that you got to do: some bookkeeping, equilibria. Everything's in equilibrium. Some are really great, right? This is a really large equilibrium. Some are actually straight up like that. Some are backwards. Others are pretty equal. And so for a lot of the reactions you do actually in 40B, so equilibrium 40B, they're going to be pretty straightforward. As a matter of fact, they're going to be like this. When they're not going to be like that when you hydrolyze ATP. Hydrolysis. It'll be one direct way. It'll be like that. What else? When you decarboxylate, decarboxylation is super stable in the body. So going from this guy, ba-boom, ba-boom, getting something like, that gas of CO2, super entropically favored. You also go from one molecule to two molecules. Entropy, huge, 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 huge. Okay. And so with that being said, decarboxylations, ATP hydrolysis is typically not uh, equilibrated back and forth. And finally, radical reactions. That's it for that. Your very final thing you should kind of know is arrow pushing. Arrow push realistically. Arrow push realistically. Typically, that means 2 to 3 arrows per push. Okay, as a general rule of thumb. You don't want to be pushing arrows like crazy because that means you're breaking and forming a lot of bonds, which is a lot of energy. Okay, that's why you can't do like 10 to 15 arrow pushes, um, because that's just straight up like energetically almost illegal. Okay, so stick to 2 to 3 arrow pushes, but be realistic too. I mean, sometimes it could be 4, sometimes it could be 1. Okay, um, a lot of simple organic chemistry is restricted to bimolecular reactions, aka two things hit each other. Two things hit. And so you're only going to get really a maximum of 2 to 3 arrow pushes. That's in synthesis. You're not necessarily in synthesis. You are in bio. And so termolecular reactions, because of the way enzymes position things, can actually happen. So you could have 3 to 5 arrow pushes in these cases. Okay? And that's about it. I mean, this is really the kind of generic understanding of things you should know for bio slash organic chemistry. Oh, and one other thing, because a lot of the enzymes that you would be discovering in this class do it, but it's very subtly referenced. and though I think it's something that should be stressed more, is metalloenzymes. Metalloenzymes, for example, your aldoses. I don't know how to spell that. Aldoses, right? They catalyze aldol reactions and retroaldol. Actually, do both. Zinc. They have a zinc active site. The zinc actually has catalytic ability because it acts as a Lewis acid. And what it does is it actually activates. It activates your alpha carbon because it's going to pull electron density. So Lewis acids, Lewis acids pull out electron density towards them. Okay, and so as a result of that, they make things more susceptible to proton exchange or whatnot. And so, for example, in an alpha carbon, where you may have something like this, Zn2 plus, and it's going to be pulling electron density away from the carbonyl. Okay, actually, I'd rather draw it like this: C H H H. And by pulling electron density, you make the polarizability of the CH bond as well increase because the oxygen is now going to be pulling more from the CH as well, right? Because the zinc is positively charged. It's going to pull from the oxygen. The oxygen, being electronegative, is going to get unhappy. And so to compensate, it's going to pull from the CHs right here, or the C bond as well. It's going to pull from those guys even harder. Additionally, once this molecule stabilizes, right, and this is why the acidity of alpha carbons can become dramatically increased or decreased, right? So pK drops and you increase the acidity. Is because it can stabilize the conjugate base really good. So this enolate can do boom and boom, and it's going to develop a negative charge here. That can coordinate pretty good with your zinc. It's not only zinc, it's sometimes magnesium. A lot of phosphatases and a lot of kinases are also metalloenzymes because they have to stabilize and make your phosphates in your ATP electrophilic. How do they do that? They pull electron density away to make a nucleophile attack. Again, something covered in other videos, but it's good to know that a lot of your things are metalloenzymes. The other thing that could happen is oxyanion hole. This is always for tetrahedral chemistry with carbonyls in 40B with tetrahedral. You form this tetrahedral intermediate, R, R, and R. Yeah, this guy right here, this O minus, is super unstable. So what does your body do? It actually gets a bunch of amides and allows it to H bond. So you actually reduce the stability, or you increase the stability of the system by enthalpically benefiting itself through weak interactions like H bonding, which in these cases can actually release about 30 kcal per mole. And so it's pretty good. Could be kcal or kj. I'm not sure. It's one or the other. That you don't have to know that, but it's a decent amount for an H bond, which it's typically like 1 to 2 in most situations. And so, anyways, without further ado, I hope this video was helpful, and best of luck on your videos, on other videos, or your academic endeavors. Thank you for watching.